Okay, so our final speaker today, just to give a short talk about a paper that he published, him and colleagues published in Annals of Applied Biology, as I mentioned at the start, which is owned by the AAB. So, Rob, if you can share your screen. Rob is joining us from New Brunswick in Canada, which is, I'm sure, a place that many of us would like to visit. A wild and wonderful place, I'm sure. And he's going to tell us about this paper, which was published. So, Rob, please tell us all about it.
Okay, can you hear me okay?
Yes, indeed, we can.
So I appreciate being invited to give this talk. This is sort of the basis of some of my other research I'm going to talk about. So this is a bit of a foundational paper for this work on management. And what we wanted to draw attention to is what we consider to be a fundamental, or what really is a fundamental concept in wildlife population management. And that's around compensation and additive mortality. And I'm going to give an example here because it's easier to explain it. So imagine in Canada, we are interested in doing some sustainable harvest, some hunting for our vast caribou populations. And intuitively, what you might think is that if you increase the mortality associated with this hunting, you're going to lead to a decrease in the population growth rates. As you increased harvest mortality, we'll call it, you're going to have a decrease in the population of deer, and that population growth rate is going to be negative. But what's true of caribou, which is true of most populations, is they have a certain capacity to compensate for this additional mortality up to a certain point. And there's various ways in which they can compensate. These are usually density dependent, meaning that as you remove some portion of the population, it leaves an opportunity for feedback mechanisms to replace those. Now, one of the ways you can do this, or one of the ways it happens, is through immigration from other surrounding areas. And you can also manage to encourage this by, for example, keeping a localized harvest or constraining your hunting season. There are also ways to just reduce natural mortality. It happens naturally if you harvest from a large population and you're really just culling the ones that were going to die of starvation, for example, anyways. But you could also do things like avoiding bottlenecks, like reproductive periods where they're very vulnerable, or populations that are already kind of threatened and at lower densities. There is some work that also looks at you can remove some of the predators and reduce the mortality in that way, though that one's not super effective. But at some point, you're going to get if you keep ratcheting up your harvest mortality, you're going to get a point where that mortality starts pushing those populations negative. In other words, you're sort of overcoming this the compensatory capacity of these populations. And this can lead to what we call additive mortality. Okay. Now it's important to this is obviously, if you are managing for sustainable harvest or conservation, compensation is what you'd like. If you're an additive mortality is what you don't want. Now, not all wildlife management is for harvest. There are, of course, a component of wildlife management is also dealing with pests, both vertebrate and insect. And in this case, you have populations often that are actually already have positive population growth rates. And what you're trying to do is reduce those populations, sort of suppress this compensation so you can get mortality that is additive from whatever your control tactic is. Ideally, at least to the point where population growth rates are zero, meaning those populations are stable. So that's the context of the biology in our question. I'm going to be talking about it for spruce buttermint. You can see here, this is a map of severe defoliation over time. This is back in the 50s and 60s. You can see the scale at which this takes place, just for reference. New Brunswick, where I work, this is about the size of Ireland, or Latvia if you're farther east right now. And you can see some of these outbreaks, especially in the 70s and 80s. These were, I think it peaked around 55 million hectares. So these are monstrous size outbreaks. And of course, it begs the question, can we even suppress populations when they have this kind of scale? And there's very good this is just a general issue, not just with spruce bugworm, but for insect pests in general, is they have a very huge compensatory capacity when you try to inject some control mortality into them. Part of it is because, like spruce budworm, which is this case, they have incredibly high fecundity. One single moth produces 180 eggs. They're also prolific dispersers, and budworm is no exception to this. This is in Quebec a couple of years ago, where they were pushing the moths in front of a building away using a front-end loader. They disperse in such densities that you can detect them with weather radar, and it looks like snow or rain. It's not the case for budworm, but for other insects, they also don't have enough natural mortality. And this is sort of the case for agriculture or invasive pests, but just in general, part of the reason we don't talk about these concepts very much in pest management for insects is because most systems are either assumed to or are not very amenable to it. And so what happens, you end up what's called a protection strategy, which is really you're just aiming to kill enough of the insects at these very vulnerable times where you can keep those plants alive or marketable until harvest. Okay, so there's no implication that your management tactics are going to lead to a decline in those populations. So let's look at this for spruce budworm. Let's say we actually wanted to test or try a population control program for it. BTK is the main insecticide we use. It's a biological insecticide applied via plane. There are ways you could actually manage populations to suppress these compensatory mechanisms. And a lot of this has been done really well with wildlife populations, of which a lot of the work I cited was from the UK. You can control immigration to some extent by using area-wide management to remove the refugia where you might get immigration from. You can reduce mortality by actually targeting bottlenecks. You can target relatively low density populations before they're competing. And you can use narrow spectrum insecticides or tactics that are not going to affect the mortality caused by natural enemies. And we actually do have a program like this, which I'm one of the co-leads on, which is called the Early Intervention Strategy, which is part of why we were interested in this question for this paper. So in this paper, we looked at the question, just a very simple question. So if we want to stop populations from growing, how much additive mortality do we need to stop population growth on some sort of over an area? And this was part of this question was a bit of a sneaky way to be able to discuss forest insect management in the context of these terms that we're using. So we use some of the foundational population data. We have very thorough life tables where we have all stage specific survival for each of these different life stages. This basically just tells us how many died within each of these periods throughout their life. We have it for multiple years. You can see this back in the 1940s. And we also have these really nice estimates of moths to eggs ratio. And basically all you use this for is if you know you have a certain number of adults, moths, and you have a certain number of eggs, if there's way more eggs than you would expect based on the fecundity that you have there, you can infer that there's been immigration into these sites. Or if it's below that, you can infer there might have been emigration. And we just put this into a very straight, it looks complicated, but it's a straightforward population model where we're using it to calculate population growth rates. We just fiddle around with the mortality rates or survival rates at different life stages that are vulnerable. So there's the egg stage, there's the larval stage, and we also varied different levels of moth immigration. Now, part of the reason this is a very simple model was we were trying to stay focused on our question. And we also didn't include what's often included in these, which is sort of a function for looking at density dependence, partly because these populations are so low that there is no competition when you're doing the management. And I'll just give there was 6 panels for this, but I'm just going to give an example of a couple of them because they all tell the same story. You can see at our different immigration rates, we have population growth rates on the y-axis, and we just basically, if we started at the densities that took place in nature, and we just started dropping down egg mort survival to a certain point, at some point, they hit this 0 population growth rate. Okay. And for the case of eggs, it took anywhere from 33 to 66% in sort of a none to low immigration condition. But you can see if you have really high immigration, you can never push that population down to stability, no matter what you do, because you just have such a huge influx. Now, the late instart larval stage, they have way more mortality. They're sort of 70 or 80% mortality to begin with. So you actually have very much less that you have to reduce that survival to get to that stable population growth rate, anywhere between 8 and 18% mortality or additive mortality, which seems much more reasonable than for the eggs. And so it's one of the points I want to make is this seems sort of an arbitrary number, 8 to 18% additive mortality. Part of the reason it's important to talk about this in the context of insect pest management where you're aiming for population control is that the additive mortality is a different number than the baseline mortality you get from, for example, an insecticide. BTK, which is what we use, you can get 60 to 65 to 70% mortality. But if all of that mortality is compensated for, it has no meaning for population management. So really the number that we actually need to know is how much additive mortality we can get from these individual tactics. And obviously immigration is the largest compensatory challenge based on our models. And part of our reason for writing this paper was to sort of create a basis for the conversation around additive mortality that we find is much more amenable for public outreach and even talking to our industry partners, because again, all the talk about insecticides is about the full level of mortality as opposed to how much you need for the actual purpose of your management program. Now, you might be asking, okay, this is a very simple model. How realistic are these estimates? As I said, we are actually running this program, and this is from our forthcoming paper. It's just in review right now. We have this really interesting scenario where they're doing that traditional protection strategy using the exact same insecticides as New Brunswick is using for this early intervention strategy. And you can see we're about 10 years into it. You can see what the protection strategy looks like in terms of hotspots, which is densities that are sort of reaching into the outbreak level, versus New Brunswick, where I work, where we're doing this population control management, where we're suppressing compensation. And we're 10 years into it. This is year 6, I think. And so the model was predicting sort of 8 to 18% additive mortality we needed. We know, based on our collections, that after 10 years, it's anywhere between 10 to 15% additive mortality is what we're getting to get these really, really nice results. So I've sort of sketched over the article. I welcome you to go check it out at AAB, and the link is there. Other work we're doing on this early intervention strategy or spruce buttonworm, more invasive stuff, which I also work on. You can find me on ResearchGate, or I welcome you to send me an email if you have questions as well. Thank you for your attention.
Excellent. Thank you very much, Rob. I mean, it showed a real great example of reusing data. So data from the 40s, which is of good quality, so that you reanalyze to come up with something which is relevant for modern times, let's say. Is it so why is there such a big gap between the data that you used then and obviously this new project that you just talked about? Was there not comparable data through the 50s, 60s, 70s, 80s, 90s sort of thing?
It's incredibly, what's really surprising is it's really difficult to get stage specific, like life table data that covers the entire length of their life. Like even my data, for example, right now, that we're collecting for our work is really, we collect a larval stage, we collect a pupal stage, we collect overwintering larval stage, and that's all we can do over a very large area. Now, this part of the reason why they were able to be so detailed was they had a monstrous staff of about 30 or 40 people. This is in New Brunswick, and back in those days, like the families, your kids and your wife worked with you as well to collect this data. And they only did it for 5 branches per site, and for just a small number of sites. So it was a very narrow data set, but incredibly precise for what it was.
And as I said, a good example of if you have some old data lying around sort of thing that you don't think is any use, then go back and analyze it in a different way, or look at it in a different way, and it might come up with something interesting. So yeah,
For sure.
Okay, so cool. Thank you very much. We haven't got any other questions coming thing, but you obviously gave your email address, and people can look at the paper and then come back to you if they have any questions. And we look forward to seeing the new version of this, I guess, getting published sometime soon, hopefully. Okay, brilliant. So thank you very much, everyone who's come along to the meeting today, both participants and and the folks who've asked questions and just listened in. As I said, these talks should be available pretty soon on the YouTube AAB YouTube channel if you'd like to point your colleagues towards them if they've missed out. And we will be having another webinar in December. As I said, will be organised by our early career professionals specialist group, and we'll look out for adverts for that coming up soon. So thank you very much to Rob, to John, and Estrella for your talks, and I hope everyone enjoy the talks, and we'll see you again soon.